Have you ever wondered how with a flick of a switch, you can literally have electricity at your fingertips? Well, unless you're off grid, that's largely thanks to your local distribution network. Over the past 3 years, I've spent majority of which interacting with them, and in this video, I'll explain their role in Australia's electricity system, the infrastructure that make them work, and why they're a major factor in the success of Australia's energy transition. Hi everyone, my name's Jack, and welcome back to the channel, where today we'll be discussing distribution networks in the context of Australia's electricity system. Specifically addressing 4 key points. Number 1, the fundamentals. What is a distribution network and who is responsible for them? Number 2, key infrastructure. What infrastructure is utilized and how does it operate? Number 3, getting out into the field to answer what does distribution network assets actually look like in real life? And then number 4, covering what are some current challenges faced by distribution networks. So with that, sit back and relax, grab yourself a coffee, let's get into it. So what actually is a distribution network? Now, traditionally their function is to facilitate the distribution of high voltage electricity from the transmission network to consumers at suitable voltages. Now, as we explored in previous videos, the primary function of the transmission network is to transmit power long distances, and in order to minimize line losses over those long distances, it's done so at very high voltages, usually within the range of 132 kV to 500 kV in Australia. As those voltages are very dangerous, it becomes a primary function of the distribution network to transform them down to voltages more suitable to household consumption. This is where you'll see voltages within the range of 66 to 33 kV in the sub-transmission network, all the way down to 11 kV for your standard distribution network, and then your 415 three-phase house supply. However, as we've seen an increase in penetration of rooftop solar and other DR out in the distribution network, a more modern day function of the distribution network is to actually operate and support reverse power flow from the consumer up to the distribution network, and even at some points up to the transmission network, flowing backwards at nodes. This has resulted in distribution networks being required to support this volatility, where networks with higher DR penetration such as South Australia can see higher load fluctuations, reaching record highs of 3.3 gigawatts on a Thursday, all to see negative demand on the following Sunday. It's really such a big swing. So who's actually responsible for operating a distribution network? And as you can see on this slide, it's what we actually call a distribution network service provider. Now, the DNSP is mainly aligned with the primary function of owning, maintaining, upgrading, and facilitating connections to the poles and wires for which facilitate the primary function of the distribution network, being to support the power flow from transmission down to the consumer level, whether it's flowing forward or in reverse. The primary roles of the DNSP, as I alluded to before, is number 1, electricity distribution, providing the poles and wires required to distribute electricity. Number 2, provide and support network maintenance to enforce reliability standards, primarily being to maintain and upgrade distribution infrastructure to ensure reliable electricity supply. Number 3, being connection services, facilitate the connections for new customers and supply upgrades for existing customers. Number 4, being to support the metering and data functions for the integration with the market. And finally, number 5, ensuring regulatory compliance. As I've illustrated on this slide, the local DNSP is largely regional. So over in WA, it's managed by Horizon Power and Western Power. In South Australia, it is SA Power Networks. Up in Queensland, Ergon manages the northern suburbs and Energex the southern and central suburbs. In New South Wales, it's managed by Essential Energy, Ausgrid and Endeavour. Tasmania is largely managed by Tas Networks, and Victoria has the largest combination, being a combination of Gemina, City Power / Powercore, United Energy, and Evo Energy. So what is the typical architecture required within a distribution network to support the primary functionality? So as we've explored in the previous slides, the general workflow for a distribution network is essentially receiving power from the transmission network into a distribution or zone substation. Now, as we'll explore in a minute, the fundamental role of the zone substation is to perform that voltage step down, effectively taking the high voltage from the transmission network and transforming it down to lower voltages expected on the distribution network. That low voltage power is then distributed on distribution lines or feeders out to consumers, and consumers, the load profile can range from primarily residential in residential areas to industrial in more industrial areas, to a combination of both. So these feeders must really be rated appropriately, and thus substations must be rated appropriately. Now you may be wondering, what exactly is the sub-transmission network and how does it differ from the transmission network in this case? So what I refer to as the sub-transmission network is effectively the higher voltage lines that are actually a part of the distribution network. So the transmission network connections are actually quite rare in the power system because there are so few transmission lines. And what is usually the case is that distribution networks are actually constructed of a web of, let's say in South Australia, 66 kV lines, for which forms its sub-transmission network in the metro. And so therefore, a lot of these zone substations are actually connected by that sub-transmission network, with a major substation actually having a connection to the transmission network. So zone substations are more commonly fed by actually the sub-transmission network, and it's more of a rarity that they are fed from transmission networks. However, the infrastructure required to support both connections is largely the same, for which we'll get into now. The primary function of the distribution substation is to transform medium level voltage, which I've tokened here as 33 to 66 kV, to level safe for distribution, which here in South Australia is 11,000 volts. So with reference to the diagram on the right, where power is flowing from the sub-transmission network at the top to distribution lines at the bottom, the common substation is designed to, number one, ensure reliability. Effectively, if one of these power transformers, which are largely responsible for doing that voltage step down, if one of these had to go out for maintenance, could we supply the rest of the load using a single transformer? And could we configure the substation in such a way to support that? Which leads me to number two, which is that simple maintainability. What this diagram shows well is the use of what we call isolators to effectively switch the power system to allow simple maintenance. So for example, let's say we wanted to take this power transformer on the left out of service. We could isolate at the high side circuit breaker and low side isolator and take this completely out of service, relying on the power transformer on the right to supply all of the load should it be rated appropriately. Similarly, on the low side, we've got things such as section breakers and isolators on each one of the feeders to allow that simple maintenance. And this is a fundamental design choice for distribution substations. As I've got on the left here, common infrastructure are circuit breakers, which are effectively automated switchgear that can be operated remotely by controllers, but can also be operated by protection devices. Power transformers, which as I detailed before, whose primary role are to step down and step up voltage, whether power is flowing in reverse back to the sub-transmission network or in the forward direction. Isolators, whose primary role is to isolate primary plant for maintenance or reconfiguration. These are largely manually operated. Metering transformers, who are fundamentally responsible for power quality monitoring, so allowing us to see readings and analysis of the substation from remote interfaces, as well as to empower the protection systems to operate. So protection can't operate on primary current and voltage. It requires a much lower grade signal in order to get those granular readings and operate appropriately. So that's where your current and voltage transformers come into play. And then last but not least, the feeder exit switchgear. Now, this can be a circuit breaker, or more commonly in the country, a recloser, for which are also remotely controllable as well as operable by protection devices, which is very important for protecting our distribution lines or feeders. So moving down the line onto our distribution lines or feeders, whose primary function is to distribute power from the zone substation down to consumer connection points. Now, speaking of consumer connection points, distribution lines are largely designed to feed multiple customers. So for example, thousands of residential customers or 5 industrial customers. However, for those large industrial loads or emergency loads such as hospitals, we do have what we call express feeders, where effectively a single load will get its own feeder. However, with reference to the diagram I'm showing on the right, this is more of your generic setup where a feeder is feeding multiple customers. So what I've illustrated with this line on the right is effectively the feeder exit breaker up the top here, and then an air brake on the way out of the substation. And then as we go down the line, you'll see different infrastructure. So on the right here is what we've got called a distribution transformer. Effectively, the voltage of this line here is what we would generally call HV, or in South Australia, 11,000 volts. And the role of this distribution transformer is to step that further down to household supply voltage. So that being 415 volts. 3-phase. And then depending on the type of connection, that is fed to the consumer. In addition to the distribution transformer, we've also got midline switchgear. So that can be in the form of, let's say, a recloser, which you guys would have experienced before but may not have known what it was. So if you've ever been in your house and the power's gone out and then it's come back and then it's gone out, then it's come back and then it's gone out, what that is a recloser actually reclosing on the fault to try and clear it, because commonly in any parts of Australia, a lot of the faults are tree branches tapping on the power line. And so what that will cause is an intermittent fault that will clear. And so the recloser will see that and operate and operate and operate. And if it goes away, then it will restore power. But fundamentally, it will lock out after a few recloses for obvious safety reasons. So that's the recloser. Similar to that is what we call a load switch. So load switches are also able to be remotely operated, similar to reclosers. And then to round out our midline equipment, we've got what's called a voltage regulator. Now, especially in South Australia, distribution lines experience what we call line drop compensation. Effectively, because our distribution lines are so long, the voltage drop, even with three-phase AC, is significant over time, and therefore, in order to maintain voltage within nominal range at the end of these feeders, voltage regulators such as SVCs or StatComs are utilized to inject reactive power to actually increase that voltage. Now, as rooftop PV and other DR on the end of these networks continue to increase in penetration, these VRs aren't required in such high volumes anymore. However, specifically in country areas, they are still routinely used. So as you can see from this diagram on the right, feeders are designed to handle really abstractly configured loads. So effectively, they're just like a big web. And commonly, feeders will interact with each other through what we call tie points. Although I haven't illustrated it here, let's say on the right here, remember back at the substation, we had 4 feeder exits. Let's say the feeder on the left actually connected to this one, and it could be switched to configure the network. Let's say if we wanted to maintain the feeder exit circuit breaker to tie the load away and keep people's power on while maintaining the assets. Alrighty, so out into the field and checking out some examples of some infrastructure I just mentioned. In this case, we've got distribution transformer. So a couple pieces of infrastructure here worth calling out. An example of an isolator is on the top here. Now it looks like these used to actually be fuses, but they are now just blades. And so to actually open these, an operator could come up and drop down this piece of metal and they would open it. Let's say if they wanted to maintain the transformer for any reason, they could then just come and open these 3 isolators. Obviously it's a 3-phase system. We've then got the distribution transformer. So similar to power transformers, but much smaller. We've then got the distribution line, which I've called the HV in this case. So the 11K distribution line. Again, 3 phases, 1, 2, and 3 just hidden behind here. And then we've got the distribution line, the LV, so low voltage house supply. So the function of the distribution transformer is to take the primary into the primary windings, and then using the internal windings of the transformer, convert that down to a lower voltage, which is transmitted to your consumer connection points. You've then got a South Australian hallmark being the Stobie pole. Now, as I said, in SA, these are very unique, being they're made of concrete and steel. However, in other states in Australia, looking on the East Coast, generally they'll use wooden poles. Alrighty, moving on to a configuration for a disconnector. So as you can see here, this actually looks like it used to be a fuse as well, but has been replaced with a straight bar. But similar to the isolators on the transformer setup, effectively these can just be opened to form an open point. Something else I really wanted to point out with this diagram is the insulators, which are the disc types in this case. So probably one of the first things I found and immediately found myself looking at every time I drove down a road was the disc type insulators actually reflecting the voltage level of the lines. And so specifically in South Australia, this is from traveling similar across different eastern states as well. The number of discs is reflective of the voltage level. So in this case, we've got 11 kV, so it'll have a single disc. If it was 33 kV, it would have 3 discs. And potentially I've also seen examples where 66 kV has 6 discs. So effectively, we won't get too far into this, but an insulator is effectively providing resistance so the power flows down the wire instead of into the power pole. And so it provides that extra distance and of a resistive material. So it chooses to flow down the least path of resistance instead of into the power pole. So moving on to the load switch. So as I spoke on earlier, the load switch is an automated and remotely controllable piece of switchgear. And so pointing that out here is good for the control box. We've then got the load switch. Looks like a bit of a spider thing that sits on top of the power pole. So internally, when it's operated, it'll actually open and the 2 connections will actually pull apart. For this to work effectively, it requires a voltage reference provided by this voltage transformer. And so similarly to the transformer setup, these have also got isolators to allow simple maintenance. However, I haven't pointed that out because we've seen that already. And the last picture we're going to go through is what I call an over-under. Effectively, it's an overhead line for which the configuration is required to go underground. And then it's going through, in this case, they are loaded with fuses into an underground connection. So these are what these wires are actually going underground here. Another thing I'd like to point out on this configuration is what they call surge arresters, which are effectively if a bit of, let's say, lightning struck this line, these surges are designed to absorb that, effectively providing less resistance than the insulator and the line. So rather blowing these surge arresters rather than getting further down. As I alluded to earlier, a primary challenge faced by distribution networks across Australia is bidirectional power flows. Given Australia's incredibly high penetration of DER on the distribution network, it actually causes certain feeders, certain zone substations, and even transmission nodes to operate in reverse flow power, meaning that they're acting as net generators. So as we explored earlier, instead of power flowing from the zone substation down to the feeder, there is sufficient DR on the network such that in certain periods of the day, primarily when the sun is shining as shown on the right here in the dark curve, the demand on the network actually is reduced because a lot of these feeders are acting as net generators. And if enough feeders within a zone substation are acting as a net generator, then the substation acts as a net generator. And that even cascades up to the transmission node, meaning that all distribution substations fed by a transmission node are acting as net generators, and as such, the transmission node is actually flowing in reverse power flow. Now, such behavior is causing large risk on the network, specifically on days where there is naturally low load. So for example, weekends when your industrial load isn't operating, effectively allowing demand to approach these really low levels, such that, as we explored earlier, generators on the network that are required to provide essential system services, such as system strength, actually have insufficient demand to operate. A credible contingency could actually cause a security violation. In addition to this, the reduction of demand or such feeders acting as net generators increases the risk of maloperation of emergency schemes such as the under-frequency load shedding scheme. Now, I spoke about this in a recent video, check that out up in the top right corner, but as a bit of a TLDR, the UFL scheme is intended to operate in a significant imbalance between the supply and demand shift that maintains the system at 50 Hz. And how the scheme works is that effectively to arrest frequency, it must trip load. And when it goes to trip load, should that feeder be acting as a net generator, it's actually exacerbating the problem. So mitigation here is actually enhancing schemes such as the UFL scheme to act differently in reverse power flow conditions, effectively dynamically arming these schemes such that if the feeder is operating in reverse power flow, it does not trip that feeder. In addition to this, specifically for the minimum demand days, tools such as flexible export limits for permissible DER are being enacted and are highly effective. So that's the distribution network, which in my opinion is probably one of the most interesting places to be at the moment in the energy sector, working at the edge of innovation to ensure customer reliability, effectively keeping the lights on whilst allowing this power system to be operated with such high levels of DER, whilst also considering what the network could look like in 10 years. It's really an incredible combination of different factors that is just forcing the DNSPs to be very innovative. So if you've enjoyed today's video and have any outstanding questions, feel free to leave them down in the description below. Things I may have covered, may have skimmed over, or you'd like to see in the future. But as always, thanks for watching, and I'll see you in the next video.